Hey, everybody. Can you all hear me? Awesome. Great. So listen, when I was coming up with the talk name, I wanted it to be bombastic, so I came up with this. Uh, so this is about weird Python. It's a few ways in which Python can misbehave. And what I hope you take away from this talk at the end of it is a few ways in which Python can misbehave, but also why it misbehaves. And are we doomed to repeat these mistakes for the rest of eternity? I don't know. We'll find out. So I'm Nafiul. I am a developer advocate at Sonar. I have been a developer for, I think, 10 years now. Actually, it's more than 10 years, which means that I am getting older. Happens to everybody. What can you say? And if you'd like to follow me, you can use whatever it is that you use over there. And yeah, that's me. So why should you care about the ways in which Python misbehaves? I guess the biggest thing is other people have made these mistakes. So if somebody else has gone through the trouble of shooting themselves in the foot, it's only good that we learn from their mistakes. I mean, we can cut ourselves in the foot, but at least we won't shoot ourselves. And I guess a bigger part is understanding why these are issues in the first place. And as I go through this talk, I'm going to show you that, you know, a lot of it is intentional. It misbehaves because it was designed to misbehave. So hopefully we can get into that. So the first one is called mutable default arguments. Now, to explain this is the talk is cheap. So let's just start with the code. We have a function called add item, and add item takes in two arguments, item and items. And item is what you would call a positional argument, and items is your keyword argument. And what we then do is we append item to items, and then we just print it out. And then we return the items. Now, if you go ahead and do this, something weird is going to happen, which is that as you keep adding a 10, and then another 10, and then a few more 10s, you see that the item list continues to grow. And then you have like a big item list, and you kind of don't want that because there are too many 10s in that list. So the reason, well, it's almost as if, you know, you have this situation where there is like this shadow variable outside of your function that keeps getting passed into every single function call that you're making to add item. And that's because, you know, default arguments in a function definition is only going to get evaluated once. That's all you get. It will not get reevaluated on each successive function call. And so how do you solve this problem? Well, you solve this problem by setting items to none, and you check for none inside of the code itself. And this value is what we call a sentinel. We check to make sure that if it is none, we set it. Now, that's a pretty simplistic view everybody knows about. Well, I hope most people know about mutable default arguments. But if we take a look at the bytecode, at the Python bytecode, we're going to see something interesting. So how many of you have used the dis module? Raise your hands. All right. So basically, Python kind of compiles down to a set of bytecodes. So if you've ever seen a .pyc file, that's where all this code is hidden. You probably won't be able to understand most of it because it's in some gobbledygook, but this is what it looks like if you use Python-m dis and then your Python file. So, okay. So we have some code here. These are effectively the line numbers. Don't worry too much that it goes from 2 to 4. But what we're doing in this particular piece of code is that we are loading fast. And what that means is that we're loading a local variable. And that variable is items. And then we are loading a method called append. Pretty simple stuff. But if we were to change it to the way that we do it here, where basically we are checking for item is none, you are going to see inside of the dis that we have this extra condition, pop jump forward if none. And what you go is from line 2 to 10. But if it is none, then what you do is you build a list, and then you store fast into items. And whenever you see an underscore fast at the end of anything, it's basically you're dealing with local variables. But why? Why does Python behave in this way? Why are we doomed like this? Why does it have to hurt? And does it have to be like this? Well, apparently, Ruby does it differently. So this is append.rb. And what you have is, well, they also use def to define functions. And you have append to array. And what this does, it takes a value. It also takes an array. It pushes, well, we call it a list. They call it an array, tomato, tomato. And then here you take array.push and you push in the value and you return the array. Now, if you print out after you append 1 to the array, you will get a 1. And if you print out 2, you'll get a 2. So effectively, they haven't made the same decision that Python has made. Why? Well, Python's way of doing things is more efficient. It avoids creating new objects on each function call. There is a bias when it comes to functions towards immutable defaults. So people are encouraged to use immutable defaults. And explicit is better than implicit, which is, from the Zen of Python. And under the hood, Ruby also uses sentiments. However, there's a downside, which is that it is a little counterintuitive. When you are starting with the language, you're like, why is this happening to me? So did anybody learn something new? Did you know about mutable default arguments? Can you raise your hands? All right, most of you did. Did you know how to fix this issue? All right, did you know why this remains an issue? Very smart man over there. And did you know that other languages did it differently? I see you. But I will impress you because I have another one. All right, so this one is about integer caching and identity. That's an interesting title, right? No, it isn't. So as usual, I will start with code, and this is inside of the REPL. That's why you have these three lines here, just to make it obvious. And inside of this REPL, I am writing some very complex code. I'm assigning A to 10, B to 10, and I'm checking if A is B, right? And how many of you know about Python's integer cache? All right, not everybody. So basically, Python, because it's lazy, it has a bunch of small numbers created already as the interpreter launches, okay? Because it doesn't want to have to create all these small integers. I don't blame it. I'm lazy too. But here's the thing. Okay. But here's the thing. The integer cache goes from -5 to 256, right? So the behavior that we're seeing is what we'd expect, right? If I told you that the cache is between -5 and 256, this is congruent with logic, correct? Okay. So if we did it in a Python file, what would you get? Would you get true false or true true? How many think it's true false? All right, a lot of you. How many think it's true true? Okay, so most of you are confused. Well, it turns out that it is true true. It is. Why? Why? I should have put another GIF there. But it turns out that if two constants are part of the same compilation unit, they will be the same object. And that is what the is operator does. It is the identity operator. It checks if this thing is the same as this thing. My two hands are different, but I hope you get the picture. Anyways, so how do you solve this problem? Well, it's not really a problem. It's not like you're going to start comparing is all the time, but it is, most of you use double equals, right? Hopefully, right? Okay, great. But if you wanted to make this work, what you would do is you would cast 999 as an int, you'd assign it, and then you'd get a false. You see? Smart. But let's take a look at the dis. You know, the dis don't lie. So here, if you do python-m dis, and then I don't know why I called it cache.py, but that's there. And what it does is that it loads a constant. And remember when I told you that Python has this integer cache and it just kind of just pulls stuff out of thin air? Like this is the integer cache working. And what you do is you store it to a name and you call it A. You do the same again with B, it's the same constant, and you store it to B. And you know, if you compare the two, they're going to be the same, right? Because it's the same constant. But when you put it through a method, well, here what we're doing is we're load name. So you've seen load fast. Load fast is when you're looking up something in the local scope, and load name is generally when you're trying to look up something in the global scope. What is local scope? Think about your function. What is global scope? Outside of your function. Okay. And that way, you can get E over here. So you cast 999 as E, and then these two are different objects. However, these two are actually the same strings because remember, Python also has a string cache. So did you learn something new? Did you know about the integer and string caches? Some of you did. Did you know about that the behavior is different from the REPL and the file? Some of you did. Did anybody know what a compilation unit was? I didn't know. I really didn't know. I basically asked one of the CPython core developers what exactly is a compilation unit. They gave me like 3 paragraphs, and I just kind of dumbed it down for the normal people, you know. And you know what? This is CPython specific. You're not going to see this behavior in every Python interpreter. So that's a wart if there ever was one. So did you learn something new? Some of you did. Some of you, okay, most of you didn't. All right. But if you haven't, I got another one. And this one is one of my favorites. This is the match case statement. How many of you have heard about the match case statement? All of you. How many of you have used it? Okay, I see nobody. Nobody used it. Nobody used it at all. Okay, great. So because talk is cheap, I shall show you the code. As usual, I have a completely pointless function called match test. Because guess what? We're testing match case statements. And what match test does is it takes this sequence thing. Anybody know what a sequence is in Python is? Okay, a sequence is like a list, a tuple, anything that just goes. Like imagine me, but as a data structure. Just keeps going. So what this is going to do is that it's going to match the sequence that we have passed into the function. It's going to match an empty sequence. Okay, there's nothing in there, nada, zilch. Kind of like your soul when you write JavaScript. And look how I'm not comparing. I'm not asking is len is equal to 1. I'm basically saying, hey, this is kind of what my thing looks like. You match the rest. And here, Python does the matching for you. So if there's one item, you print a list with one item. If there are 2 items, you print a list with 2 items. If you don't know what to do with it, you just print something else. Pretty simple, right? And of course, at the end of the day, you print X and Y. Now, because we assigned X and Y to 10 and 10, you probably think it's going to print out 10 and 10, right? No? No? You guys don't trust me? You don't trust? Come on, fellas. What's going on here? Okay. It's actually 3 and 4. It's 3 and 4. And the way you solve that is basically you whenever you're pattern matching, use underscore. Underscore is kind of a special variable in Python. Like if you use the REPL a couple of times and you just, you know, A is equal to 10, and then you type in underscore, it will give you 10 because it's always the last thing that was there. Well, that's how it works for me. I don't know if it works differently for other people. But you ask yourself, why does it do this? Why does it assign inside of your case statements? That's me. Anyways, Well, I'm going to show you something else, because a lot of the times we lull ourselves into this situation where we think indentation means scope. Okay, so I'm going to show you something that has nothing to do with the match case statement. It's the with statement. And this is something that I copied from the PyTest documentation because I was too lazy to write my own code. But anyways, the thing is, if you see here, PyTest.raises runtime error as exception info, okay? They shortened it. And if you see, this is my contribution, you see. This is the line, this is the indent, okay? And then here, if you go into the assert, you still have access to exception info. Now you might say, you know, these PyTest people, you know, they do TDD and other voodoo. I don't trust them. I don't write that code. I bet you write for loops, right? I is 9. You still have access to the variables outside of the for loop. So indentation does not always entail the creation of scope. This is something that I had to learn the hard way by creating a Heisenbug in one of my applications. Don't tell anybody. But anyways, this isn't something that is universal. Okay, so for example, this is a match case statement in Rust. How many of you have done Rust? All right, nobody has done Rust. Great. So basically, you got your match keyword here, you got your cases here, and you're going to see that we have y over here. Y is only local to this block. It is not available here, and it is not available here. And no, if you write comments in Rust, it doesn't magically create variables. That's not a gotcha in Rust. So, did you learn something new? Did you know about assignment in case statements? One, okay. Well, you know, you would know. Nobody else did. Okay, did you know how to fix this issue? Okay. Do you know why this remains an issue? And did you know that other languages did it differently? Yes, okay. This guy does Rust. All right. If you weren't impressed by that, I got another one. And this one is called late binding closures. And late binding closures, effectively, anybody know what a closure is? Okay. Okay, most of you know what a closure is. Actually, no, you don't. So a closure is effectively a bit of scope. Let's just keep it simple. That's effectively what a closure is. And as usual, I start off with some code. And this is the times table. And this is the kind of software that you write in Silicon Valley. And what you're trying to do here is effectively return a list of functions that can be executed, right? So we have f of 5 for f in times table, and you're supposed to get 0, 5, 10, 15, 20, 25, 30, 35, 40. And then because indexing goes from 0 to 9, we don't get a 50, we just go to 45. So to facilitate that, we have a table. We have a for loop. And inside this for loop, we have declared a function that takes in x, which in this example would be 5. And then we just multiply it. Pretty simple, right? And then we just append this function to the multiplier. And then we return the table. But if you ran this, and this is not because I'm using VS Code, you'd get just a bunch of 45s. Not what we wanted, you know? All this time, we were trying to create a simple times table and we failed. Well, you didn't fail, I failed. So the reason why this happens is because the lookup of the value of I will always be the last value of I. The last value is 9. And as the range goes from 0 to 9, the lookup happens when the function is called, not when the function is created. And so how do you fix this? You fix this by capturing the I as a default argument, because remember, default arguments get evaluated once. When? During function creation. So this forces the value of I to be captured for this particular function. When defining a function in a loop, make sure to pass in variables from our outer scope. Now you might say, this does not impress me. And you'd be right. I mean, who creates timetables? But this is some guy does apparently. So this is a function that takes in an image. It applies a few Gaussian filters to it, and it uses a couple of secret sigma values from outside of the function scope. So if you take a look here, these are the blur operations. We're using a lambda. We're using Gaussian filter, passing in sigma, and we're passing in sigma from the outer scope. And this problem isn't only for normal functions. This happens to lambdas too, you know? Lambdas are functions. Some people just call them lambdas, but they're lambda functions. And so the way that you would pass in something from the outer scope is just basically add it as a default argument inside of your lambda, like so. And you can do that. And this works. I know it works because you can see the image that it produces. So what we were going for is like a little bit of a frosted glass image, you know, something like a little blurry, just to give it a little bit of pizzazz. And on the left-hand side, is this my left or your left? Anyways, one of them is really blurry, and it shouldn't be that way. We don't want blurry images. We want only slightly blurry images. But you ask yourself, why? Why does it have to be this way? And it turns out that other languages have done what we have done. Actually, it's not that exactly that other languages have done what we have done what other languages have done. So if you take a look at Python, Ruby, JavaScript, and C#, they have late binding. And no late binding for C# and Haskell as well. Yes, I did say that. And the reason for this is it's more efficient. Early binding might require you to create copies. No manual passing. Variables outside the code cannot be used without passing it in. And simplicity. If we wanted to add early binding, it would need to result in some changes to the language itself. But the cons are it's a little counterintuitive. And just to show you, this is actually how it's done in Haskell. If nothing else from this talk, I will explain Haskell to you, you will understand it, and then you can say, I know Haskell. So what you have here is a module main where you got the times table. And in the times table, you basically just say what the types are going to be. Like the first thing, you just say what types are going to go in and out. Okay. And then you define the function. So it takes n, and this is kind of how you define a lambda. You see this bracket and the slash over here? That's a lambda in Haskell. Don't ask me, they decided it. And if you pass in this x times I for I 0 to n. And that's effectively a list comprehension with a lambda in Haskell. And so if you create a 5 times table and you want to know what 3 times 5 is, you get 15 over here. Pretty cool, huh? So did you learn something new? Did you know about late binding closures? Did you know about how to fix this issue? Did you know why this remains an issue? And did you know that other languages do it differently? I need to talk to you later, man. Maybe even send a hit squad after you. But if you're not impressed, I got another one. And this one is about numbers. Now you know this. You're all smart people. 0.1 plus 0.2 does not equal 0.3, right? This does not work. So what do? You use isClose, correct? Use isClose, and if you use isClose, you're going to get true. If you minus, you're also going to get true. But is this going to work? No, it's not. And the reason for this is NumPy is better. So whenever you get a chance, use NumPy. But the actual reason is because there is a special value called absolute tolerance, which NumPy has specified to 0.000008. I'm not going to say all those zeros, but you get it. And if you actually see the result of this, this is what you get. It's actually 0.17 zeros and then a 2. And this is what 1e minus 3 looks like. And so if you set the absolute total to 0.0.0.1, where you don't care about this kind of difference, you get a true. But you might say, no, I shall use decimals, because decimals, I'm a smart person. Decimals will completely work. And it doesn't. This doesn't work either. This does not work either. And so at this point in time, you might be surprised. And the reason is because decimal of 0.3 is actually 0.29 something, something, something. And so the way you do it is that you have to get on your inner JavaScript and put these in strings. That's the solution. So you might ask yourself why? Because numbers are hard. It's really that simple. Numbers are hard. 1/3 in decimal is 0.33333. We can't really represent it. And this is what 3.14 looks in binary. We can't really represent it. So what should you do now? Now that I've shown you all these terrible ways in which Python can behave. Well, use some tooling, use a linter, use an analyzer. We make one, just saying. And put some heuristics in your CI and CD. And if you like having a look at all these crazy things in which Python behaves, there is actually a WTF Python repository on GitHub. And if you'd like to play with some of this code, there is an IPython notebook on my GitHub as well. Actually, not my GitHub, my company's GitHub. Anyways, that's all, folks.